We'll go to the side presentation. As we've seen, the story about the noise and the substitute source. Okay. So, now we want to measure current, to measure voltages. There are several here. These are all home, you can pass them around. All home roads. Current probes. This is one more here. You need a coil. So the one you have in your hand there is a coil inside this metal thing, plastic tube with 90 turns of wire wrap wiring. And you need a cord to be able to close this. This closes so that you get a closed Faraday cord, and then you can put your wire, whatever you want to measure, inside it also, like a transformer, current transformer. Or the other one is you take a ring and you bind it with wire, usually completely, to get maximum output. And then the difficulty here is that if you have a cable, then you have to put it through the hole if it doesn't fit. So that's why I built a big one, that you can have an IEC connected for power through that one. And the small one, yeah, you need BNC maybe. BNC will fit in this. The small one. With the right assembly. Yeah, nickel induction, you've seen that. This is a sniffer probe, which is a small C-core. It's an open one because you can use it to hold on top of a wire and you can measure whatever current is going on, whether there is a current there. You can try to find it. It's about 3 turns or 5 turns, whatever fits on the little core. Wire wrap wire again. Now, this works on changing magnetic flux. All these things work on changing magnetic flux, but for this probe, the mill standard calls it a B-dot probe because it's a derivative of the magnetic flux from time to time. So a B-dot probe. This is a B-dot probe. And then later we'll see the electric version of it, and they call it a D-dot probe. It's because it works on dielectric displacements. Okay. Now, see this? If you have a very small distance between your probe and your field, then you can see that if you move your probe, you get a different value for the flux. You move it, and you get very close to this loop. So if it's so close and you want to calculate, you have to integrate. But that's not so relevant for this story. You can probe like this. See it now. Okay. A loop probe, a single turn. Coax usually with a air gap opening in the shielding somewhere, otherwise it would be completely shielded, you wouldn't measure anything. It would be 50 ohm at the end here, and then on the other side, but this is actually just a turn, and the shield is connected here. Opening to make the inner wire reachable by magnetic field, but it's shielded for electric. And then here it goes for your equipment, which is also 50 ohm. So that's a chip here and a chip here. Well, this is the ideal probe. If if you buy these things commercially just for sniffing, then usually this is just connected, no 50 ohm. So you get some reflection, but okay, nobody cares, right? So, but if you want nice, you go high frequency, you want to see what you want to see, then you need to have 50 ohm for, let's say, 10 dB, dB, and you will be a resistor. Okay, and you can measure here, and here you measure the flux, the integrated flux over this area, which would be at a large distance. If you have the B magnetic flux density times the area is actually the same as M times I. M times I is flux, and B times A is also flux. Those ways to approach it. Simplest storage anyway. B times A is the coupled flux, and then the other example, M times I, depending on which way you look at it. Then the current flow, so the one that passed around. We want to measure a current. We use this device. The device looks like this. It's a coil. It has this substitute source produced by the neutral induction. So the coil is also there. You can measure it with the LCR meter. So you should measure it, and you use a resistor, which is usually mounted at the end of the line on the oscilloscope. So this is our model. You can calculate. Use this voltage with the L, the R, and you can calculate the out. I think that would be difficult for you next week. Also, so but just you can skip it. We have a graph later. So this is the equation you get. You just use Kirchhoff, voltage law, current law. You get this. For very low frequencies, then where this is small, this is big, this goes away, this is 1, so you only have that, right? This the omega mi, which is actually your substitute source, which increases with frequency. Okay? This one is when this gets very big, then this goes away. And this falls away to that, and you only have this and this. See? There, Frits.